Hello, Physics 30s. It's your last lesson, Lesson 7 of Unit 6. This is my favorite lesson in not only the course, but all of high school. This is the best lesson you're ever going to have. I hope you think so too. It is by far the most mind-blowing. It'll destroy all of your preconceptions of what you thought was true in terms of atoms and particles. So let's get into it. So we looked at particle accelerators and particle tracks and how those are made and used by scientists. And one of the most important uses that they have is this discovery of new subnuclear particles. By colliding high energy particles with one another, you can actually break them apart and observe all of these new particles that we could never observe naturally in the world. So this is quite groundbreaking, and it leads to an amazing intricate field of science, our particle physics. So the scientists who began doing this, I believe it was in the late 60s that much of this work was happening, started organizing all of these hundreds of new subatomic particles that they were discovering, and they organized them according to fundamental forces. I've attached a TED-Ed video that goes a little bit more in depth onto this idea and the standard model and how it's organized. You don't need to memorize that, but it is a nice video for you kind of just to dip your feet in and understand some of these particles more. So these fundamental forces, right, we have 4 fundamental forces. There's a crash course series on this as well if you want to dig more into it. The strongest of them is strong nuclear force, and that is what we find inside of a nucleus. This is what holds our protons and our neutrons together. We also have electromagnetic force, which is the second strongest, and this one is actually closely related to these field particles as well, and photons. Then we have weak nuclear force, which we will get into a little bit more in depth today. It has to do with turning protons into neutrons and neutrons into protons. And finally, gravitational force, which is kind of the missing piece or a bit of a gap in the standard model. But they're starting to get more understanding with the Higgs boson particle and different theories that are coming from that. So this is the 4 fundamental forces. If you desire to throw those into your old memory bank, they might come in handy later. They might not, but they are the 4 fundamental forces of the universe. Now we have 3 major categories of particles. The first is a lepton. This is actually the bottom rows of the standard model that is shown in the TED-Ed video. This is our electrons and neutrons. I might have labeled that number 2 and hadrons number 1. Doesn't really matter the order though. So leptons are electrons and neutrons. They do not experience strong nuclear force. They're not bound to the nucleus. They don't experience that strongest fundamental force. They are true elementary, or another way to call that would be fundamental particle. So protons and neutrons, we'll see in a minute, aren't actually fundamental particles. There's something smaller than them. They can be broken down into smaller components, but these leptons, electrons, and neutrons are not divisible. They are true elementary or fundamental particles with 0 size and no internal structure. So they are just, I don't know how you want to think about it, energy, mass, if you look into it a bit more, neutrinos actually only have 1/1,000,000th the mass of an electron. They do still have mass, but they are often referred to as ghost particles because they are so hard to detect, so untraceable, so small. They also have no charge, so obviously a ghost particle is a good name for them. And then, of course, we've been working with electrons for years now, but now we can classify it as an elementary or a fundamental particle, right? Next, we got hadrons. So leptons and hadrons, where hadrons are our protons and neutrons that experience strong nuclear force. Right, so nothing really new there, just a new name to categorize them. We could, before I think we were calling them our nucleons, so this would be just another name of a nucleon for the nucleon. And then we have field particles like photons. So these are, they could be different fields, right? It could be electromagnetic field, like a photon. It could be gravitational field, right? We've got magnetic fields as well, electric fields on their own. All of these different fields are going to have different field particles associated with them. We don't need to get into the classification of them, but it is a good idea to kind of know that that's the third category, are field particles. And they aren't only these force fields, they're also the carriers or the mediators of those forces. So they're how these photon would be a carrier of an electromagnetic force, for example. Right? Hopefully that's not too mind-blowing yet. It's going to get even better. So we now have particles and antiparticles, matter and antimatter, and kind of an intro to that. So particles, all subatomic particles, have associated antiparticles. So it doesn't matter what we're looking at. Electrons, even protons and neutrons, even neutrinos, antineutrinos, they all have antiparticles that are identical in every way but have opposite charge. So an antiproton would have a negative charge. An anti-electron would have a positive charge. But there are some other advanced properties that we don't have to worry about. So just assume that they are identical in mass and size and absolutely every way with an opposite charge. Interesting thing happens when these two collide. They annihilate each other. They're just gone. But according to conservation of mass energy, that loss in their mass has to go somewhere, and that is going to create gamma photons. So when it's an electron and a positron, right, positron would be the anti-particle of an electron, they're going to annihilate each other, and in this case create two gamma photons, which have a conservation of mass energy. So the initial energy comes from the energy in the mass of the electrons, right? Our first formula in our quantum mechanics and nuclear physics section of our formula sheet. So once we have any change in the mass of the electrons, we're going to have a change in energy. And the final energy is going to be from those gamma rays. So the mass defect of these annihilated particles will be equal to the energy carried by the gamma particles. And there's a good example on the next video walking through how to actually go through these conservation of mass energy steps and to determine, in this case, the frequency of those emitted gamma photons. All right. Now we got quarks. There's no such thing as quarks and quarks. We just got quarks in physics. The Canadian talk show Quirks and Quarks may have thrown you or some people you know off a bit, but all we got in physics are quarks, and these are what are making up our hadrons, our nucleons, our protons, and neutrons. So every neutron, every proton is made by a combination of quarks. We have two types of quarks. We have up and we have down. So to account for the internal structure of neutrons and protons, scientists needed to find different kinds of quarks, up and down. Here's how we write them. Up is just lowercase u, down is lowercase d. Their charges are as seen here. Up quark will have a positive 2/3 of an elementary charge, and a down quark will have negative 1/3 of an elementary charge. And we'll see that when we combine them, protons with two up quarks, right, that would be positive 4/3, or 4/3 minus 1/3 gives us positive 3/3, or positive 1. There's our charge of a proton. And a neutron with an up, down, down charge balances out. We got positive 2/3 minus 1/3 minus another 1/3. It's neutral. Our charges cancel out. There are other types of quarks that are talked about in a little more depth in the TED-Ed video. We've got strange quarks, charmed quarks, bottom quarks, top quarks. And those are all very massive, very unstable elementary or fundamental particles that will quickly decay and form up and down quarks. But we can observe these during high energy collisions, or in the sun. Lots of different places these can exist. They just won't last for very long. And just like all of our other particles, quarks have corresponding antiparticles, antiquarks, which have opposite charges. And that's where our second example in the video comes in. We're looking at a pi meson, or a pion, I don't know how to say it, with an anti-up quark and a down quark. Right, so check out the video for that. That one's pretty simple though. Anti-up would just mean negative 2/3. Down would be negative 1/3. So we've got negative 3/3, or a charge of negative 1. Easy as that. All right, looking back at, I think it was our second lesson in this unit, we looked at beta decay. Now we can look at it with a little more clarity. So when we have beta decay occurring, we know that a neutron, so that's an up, down, down with a neutral charge, will decay into a proton. Whenever we have protons and neutrons swapping places, we know we have our weak nuclear force at play, and it'll be, so that would be, that arrow symbolizes the weak nuclear force occurring or manipulating our neutron into a proton. As that down quark is replaced by an up quark, we still need conservation of charge, conservation of mass energy. So as a result, going from negative 1/3 up to positive 2/3, our conservation of charge requires this electron to be emitted. And we have our antineutrino, our ghost particle, that pretty much is created by any reaction at the subatomic level. And there's another video that you can see attached about how it can tell us a lot about what's happening in deep space, but they don't tend to interact with matter, so they're really hard to observe, thus ghost particles. So our beta particle is essentially an electron, which is a fundamental unit, and a neutron is emitted, which is a fundamental unit, and we got just this swapping of up and down quark via weak nuclear force. And beta positive would just be the opposite, where we have a positive beta particle, which would be our positron instead of an electron. And instead of an antineutrino, we have a neutrino. We don't need to know why this one has a neutrino and this one has an antineutrino, but it does. And that's it. We're going from proton to neutron, giving off a positron. So here's a good way to kind of identify the difference between particles and antiparticles. Antiparticles will always have this line on top. We used to use it as a vector symbol. Now with subatomic particles, we'll use it as an antiparticle symbol. You could think of it as being the negative or the opposite charge. It's not always going to be negative. It'll just be the opposite. So with that, you hope your mind is sufficiently blown. This idea of even smaller particles and this new discovery of quarks that are even smaller than protons and neutrons, and how protons and neutrons can be turned into one another using weak nuclear force. I assume that your brain is needing a little bit of a recovery after all of this mind-blowing. But I hope you enjoyed it as much as I did. I hope you enjoyed Physics 30, and I am glad to have shared this journey through the history of physics with you. It's not over. I hope it's not over for you. Continue learning always, and watch fun YouTube videos, learn about relativity and string theory, and the next physics theories that'll change everything for you in your lifetime. It's never a bad thing to be curious and want to know more about the universe. And I hope that's what you can take away from Physics 30. Alright everyone, thank you so much. It's been a blast. We will be in touch, I hope. Take care.